Welcome to this video. It's about Oemof.Solph and the storage investment optimization. Oemof is the open source energy modeling framework, which you can find on GitHub. And today's subject is about, generally speaking, finding the optimal asset configuration for my own energy system. Thus, for example, if you know that you have a certain consumption pattern and you want to find out which assets are the most economically feasible to install and how much to install, this is the right video for it. These are the sources. As you can see, it's all on GitHub. You can check it out. Of course, you should not, or I would suggest that you do not go into the dev tree, but that you check out the last stable release. I think it's 0.52. And you can see that there's an example. It's called the storage underscore investment example, and this is the example we are going to discuss today. On the keyword of the nominal value and the investment for the storage object, please check out these issues you can find here because there are some changes going on and thus you might want to be on top of the game in case you're watching this video at a later point. The energy system we are looking at today is an energy system composed of three different sources. We have a gas resource, a wind resource, and a PV resource. The gas resource is providing us with the natural gas bus, which is then fed into a power plant, which is converting this gas into electricity. Wind and PV are producing electricity directly according to the availability of wind and solar radiation. On top of that, we have a storage component, which is in this case a battery or an electric battery or some sort of electric storage, which is fed with electricity and is returning electricity. And we have one sink, basically, which is our demand sink. In the background, we have a second sink for surplus electricity, but simplified here, you can see that we have a certain demand, which is then uh, satisfied using either the renewable energy sources, wind PV, the fossil energy source gas from the converted by the power plant, or it is fed by the storage we are providing. This is how you will find the energy system explained in the code. It's basically the same as before. This is the input data of PV and wind availability. As you can see, the values are normalized. Thus, the values between 0 and 1. This is the electrical demand curve. You can see on the x-axis the hours of the year, on the y-axis the electrical demand in kilowatt hours per hour, so you can also say kilowatt. And you can see that the maximum electrical demand is around 37 megawatt. The peak demand is around 36.9 megawatt and megawatt hours in an hour. So, and the total electrical demand is 225.5 gigawatt hours. So basically we have let's say a large city, or we are having a large industrial consumer, something like this. Now, if we go into the code directly, you can see that we first have to prepare the input data file where we are also accounting for potential error on the file. And in this case, we're producing a Panda data frame with, with two values each for one time step to make sure that we have some values to optimize. If you go to the next lines, you can see that the logger is initiated. You can see that the time index is created based on it's creating the 8,761 time points, which is the number of intervals in a year plus 1. And the default interval is 1, and because Oemof.Solph is basically assuming that you are working with hours, which in our case is the case. The gas price is set to 4 cent per kilowatt hours, or 0.04 euro per kilowatt hours. It's basically just monetary units, and it could be anything you want it to be. Next, we are setting the financial input parameters. The annuity is a function which is called, you can check it out on the right side, which is called in a subpackage. It's basically just to make your life a little bit easier. And you can assign, or you can define the three values. the number of years the investment is used, so the economic lifetime. In our case, it's 20 years for all the assets available. The CapEx, so the capital expenditures per installed unit of capacity. So in the case of wind, it would be 1,000 euros per installed kilowatt of wind capacity, wind power capacity. In the case of PV, the same. And in case of the storage, which is a little bit different, we are assuming that it's 1,000 euro per kilowatt hour of installed storage capacity. This 1,000 euro includes the costs for the input power and the output power capacity. More on this later. Here we are creating the natural gas buses, the electricity buses. We are adding it to the energy system. We are creating the excess sink, which is equivalent, for example, to feed surplus electricity from renewable production into the grid. We are having a gas commodity, which is then linked to the gas bus. And we have wind, wind production setup, which is where we have a fixed production based on the data of the wind. So this is the normalized values. So wind production is somewhere between 0 and 1. You can also think about it as a percentage, that sometimes you have 50% wind production, sometimes you have 100% wind production, and then sometimes you have 0% wind production. And this value is then multiplied with the nominal value. And here in this case, the nominal value is subject to optimization. Thus, we are calling the investment function, and we are feeding it with the information on the costs. In this case, it's what we defined with the EPC underscore wind. So basically, it says, tell me how many kilowatt of wind I have to install. Whatever I install is then producing, let's say, 10 kilowatt times the nominal value in this time step. The power source PV is also basically designated in the same pattern. And similarly, the demand, however, with one difference, in case of the demand underscore electrical time series is not a normalized time series. So it tells us how many kilowatt hours we are consuming per time step, and thus the nominal value is set to 1. The gas power plant in this example is not part of the optimization. It's set up similarly to PV and wind. However, we see that the nominal value is set to 10 terawatt, which is quite a lot. And the point here is just to provide sufficient energy at every point in time. You could also set it at a much lower value, for example, 400 megawatt, which would also be sufficient and it would not affect the results of the optimization. But we keep it like this since it's also like this in GitHub. The storage component is at the center of the optimization here, or it's at the center of our interest. It is fed by electricity, and its output is also electricity. As you can see, the invest relation input capacity is set to 1/6. This means that the storage can be emptied and filled within 6 hours. More on this later. The inflow conversion factor is 1, and the outflow conversion factor is 0.8. So of every kilowatt hour you charge, 80% is being discharged and 20% are assumed to be losses within the system. What is subject to optimization here is the investment parameter, so meaning how many kilowatt hours of storage capacity do you want to install. It's defined, it's fed by the EPC underscore storage we have defined earlier. In our case, 1,000 euro per kilowatt hour, assuming that it covers the costs per kilowatt inflow power capacity and outflow power capacity. We then add all these components to our energy system and then run the system. If we run it with the standard parameters, meaning 1,000 euros per wind, 1,000 euro per kilowatt PV, 1,000 euro per kilowatt hour of storage, and a gas price of 4 cents per kilowatt hours, we are seeing that the optimal output is to install 456 megawatt of wind capacity. We don't see any investment in storage or PV because it's too expensive relative to the other options. We do see that 51% of our electrical demand is covered by renewable energy. And please note here that the investment in this case refers to installed capacity and it's not a monetary value. If we are now changing the gas price to 8 cents per kilowatt hours, meaning we're doubling the price, we see that we now install 667 megawatt of wind capacity and 189 megawatt of PV capacity. We don't see any investment in storage because it's still too expensive. And we see that 64% of the demand is now provided by renewable energy, which is nice, which makes sense since the fossil energy is now being more expensive. If we, on top of this, increase the gas price even further, tripling it to 12 cents per kilowatt hours, and we're reducing the costs of a battery or of the storage system to 300 euro per kilowatt hour of installed capacity, we are seeing that now 755 megawatt of wind is being installed, 503 megawatt of PV, and 0.308 gigawatt hours of storage, meaning 308 megawatt hours of storage. This allows us, in our example, to cover 75% of our renewable energy. As you can see on the left side on the results, we have electricity to storage, which is 51,390.71. And if you look further down, we have storage to electricity, which has the same value. This is to be interpreted as follows. It's 1/6 of our installed capacity. Since we fixed this ratio, the input power capacity and the output power capacity both are equal to 1/6 of our installed capacity, meaning we have 51 megawatt of input power capacity and output power capacity for our storage system, charging and discharging our storage system, which has 308 megawatt hours. So, as a bonus question, let's turn to the question how we can scale the different storage dimensions. If we zoom in a bit, we see that storage is not just one size. Storage actually consists of 3 different dimensions. It consists of the storage capacity, the input power capacity, and the output power capacity. Meaning, if you imagine it like a building or like a tank, how large is the tank? How large is the pump which pumps the energy into the tank, and how large is the pump which pumps the energy out of the tank? For these 3 dimensions, we can define different CapEx costs. So we're defining 200 euros per kilowatt hour of storage capacity, and for both input power capacity and output power capacity, each 50 euro per kilowatt. This allows us to optimize the size of our storage system according to our needs. As you can see, we have to firstly define the costs, as similarly like we defined them before, and we create 2 new variables for this, the EPC underscore storage, input capacity and output capacity. And secondly, we now turn towards the storage component, and we have to now account to optimize the input flow, which we do here using the costs of the input capacity, and the output flow, doing it here using the cost for our output capacity. We have to deactivate these fixed relations because otherwise there would be no point in optimization and we would just set it to 1/6 of our installed capacity. This doesn't make a lot of sense here. If we now turn it off and we look at the results we're getting, it's quite interesting. As you can see, with these new parameters, we are installing a little bit less of wind capacity and a little bit more of PV capacity. The storage size is defined much larger because now we have a lot more flexibility to adapt the storage system to our needs. So we set it to 755 megawatt hours, and the size of the input power and output power is set to 150 megawatt input power and 128 megawatt of output power. With this setup, we're able to cover 78% of our demand with renewable energy and the storage system.